Thank you to the Martins for the invitation to be here. It's very nice to be in Frankfurt City as opposed to Frankfurt Flughafen. I appreciate this opportunity. Thank you all for braving the early Friday morning to be here. And I know you are tired, so I'll try to give a somewhat more elementary talk. I'll make sure to say a few wrong things, just so that it's more amusing, but also because I planned to. And please correct. There are people in the back who I can barely see, and who I can see somewhat well. But I have no idea what you can read on the blackboard. So it's your job to tell me to write twice larger if that happens. I hope at least somebody in the back will maybe tell me. Okay. So I wanted to focus on a very naive question. This is somehow a motivational question and not how you should think about math. Maybe. So suppose X is a quasi-projective variety. And you want to know how far is X from being affine, say, or from being projected. So of course we have to negotiate what we mean by how far we are from being affine or from being projected. Yes, I know what it means to be affine. Yes, I know what it means to be projected. But how far are you from one to the other? And that's a matter of debate. You can try to compute homology events and you can do other things, but perhaps one of the most naive things you can do is you can measure something which I'll for now write maximal dimension of a compact, complete, if you wish, subvariety of X. That's one thing you can measure, right? If the maximal dimension of a compact subvariety of X is equal to the dimension of X, maybe X should be irreducible technically, then of course X is projected. Very good. If there are no compact subvarieties of X at all, well, we know this holds for affine varieties, but that's not if and only, right? You can measure this, or you can measure the same, but through a generic point of X, which you could argue is maybe even a better measure of properties of X and the maximal dimension of a compact subvariety. Maybe there is some very special compact subvariety somewhere, but there aren't any other compact subvarieties, not something like that. So you can do these two things, and now comes the most important moment of this talk, which is the vote. What should we denote these things? They don't have any notation standardized in the literature. So I would write max dim C generic of X and max dim C of X, right? I agree. I've seen a paper where one is called R, the other one is R twiddle. And it's impossible to remember which one has a twiddle. That's not going to work. So how about A and B? Okay. I'll forget which one of these is which is B, so I'll write this probably. So the point is, of course, you have the inequality this way, right? And this is equality if and only if X is projected. This is something else. I don't really know what this equality would mean. It's some interesting property, right? But I don't have much to say. So that's the question I'd like to study, but this is about moduli spaces. So the case I'm most interested in is going to be AG, which is going to be the moduli of principally polarized abelian variety, which has, luckily for me, appeared on this blackboard before. So I won't define it, but I'll remind you perhaps that this is the quotient of the Ziegler-Lapa half space by the complexity group. And if you forget what the Ziegler-Lapa half space is, I won't tell you, but I'll write a different formula, which emphasizes the symmetric nature of this space. Okay. When I write this, this means I'm writing this only over the complex numbers, which is going to be my, okay? So there are many more notions. Yeah. Say it again. Yeah. Where they go through generic tangent spaces, also then very reasonable how many points you can separate. I mean, what dimensional subscheme you can contain. There's more refined work, right? So here I go for a generic point. You can ask to go for a jet of length scale, which is very reasonable. In these situations, it's not going to be so different because my space is symmetric. I can often add. In general, there are many more now. This perhaps are two easier ones. And in any case, these are the ones I have something officially to say about. It could be some more can be. Okay, so that's my space of interest. But there is also another space that has also appeared on this blackboard, MG, moduli space of curves, of course, which you know can be embedded into moduli space for Bill and varieties by the Torelli map, which sends a curve to each Jacobian. And of course, in polite company, you don't write embedded. You say this is a 2-to-1 map of stacks that branch over the hyperelliptic locus. For this, the second, it doesn't matter, right? So I'm talking about four space, so I'll almost have to write that. You know that the image is not proper. This was mentioned before by Rahul and discussed in detail, of course. So this is injective, but it extends to a map from MG compact type. And Rahul wrote P, I'll probably do that, which maps to AG. And if you think about the Torelli map, this actually ends up in the so-called indecomposable locus. So let me tell you what this is. Indecomposable. So this is the locus of principally polarized abelian varieties, which are not products with polarization. So you take abelian varieties, which are products of lower dimensional. Okay. And you know that the Jacobian of a smooth curve is an indecomposable abelian variety. You can divide it into this. So at the end of the day, I have four spaces on the blackboard, which are open. Let me tell you a little bit about what's known. I mean, let me not tell you a little bit. Let me tell you all that is known about these two methods for this subvarieties. So what I'll do now is I'll write a big table with results. But before that, let me state the two theorems where the table really comes from. So a theorem. This theorem is due to Thiel and Sadun. It appeared in print in 2003. Of course, the archive version was a bit earlier. It says the following: for any G at least 3, the maximal dimension of a compact subvariety of AG, and I will use this because we don't have to remember which one is A, which one is B in that way. Sorry, is at most G times G minus 1 over 2 minus 1. Okay, let me remind you that the dimension of the moduli space for abelian varieties is G times G plus 1 over 2. And here it's important that this is false over FP. So this was surprising because over FP, so there exists X inside AG over FP compact, whatever you want to call it, of dimension 1 time. Okay. And this is actually the maximal possible dimension, as is quite easy to see by thinking about the lambda G class. So that's the result of Thiel and Sadun for any genus at least 3. From now on, I will only talk about genus 3 and higher, just because 1 and 2 are exceptional. Nothing interesting happens, everything is known. It will be annoying to me to only try genus at least 3. Okay, so that's the result of Thiel and Sadun, and that's the best known result in this direction that has been there. Their result is a bit more precise, and I'd like to write a more precise version. It says the following: if X inside AG is compact, and if you take the class lambda I, this is the PI of the Hodge bundle, so Rahul, of course, has written this class on the blackboard, and restrict it to X, and you get 0, then the dimension of X is strictly less than I times, or the way I'm writing this, for I at least 3. Okay. So this theorem is a special case of this theorem by taking I to be G, because you can recall from Raoult's talk that lambda G on AG is just 0, right? So it vanishes in any compact subvariety of AG. You plug in G here, you're done. Okay. I did want this case because it's a here. This is all that is known about the bounding from above the maximal dimension of compact subvarieties of AG. How about bounding from below? So here is a remark. If I have, let's use Z for compact subvarieties. Because X is a general variety. So if X is quasi-projective, it's inside a compactification projective, such that the codimension of the boundary is equal to D, then the maximal dimension of a compact subvariety for a generic point of X is at least G minus 1. This is an easy observation, right? You just, X bar is projective. The boundary has codimension D. So you just need to avoid, so you just slice X bar by generic hypersurfaces in projective space of sufficiently high degrees to sufficiently general point, so that you avoid the boundary as much as possible. So you take one hypersurface so that the section of the boundary will be dimension minus 1, and then by the time you're here, this is no intersection of the boundary. Okay? This then, this implication is absolutely false by looking at e to the A times e to the B, right? So somehow B here is completely immaterial for the dimension of compact subvarieties, and the dimension of the boundary is the B. Okay, so that's a remark, which means that I can say something about maximal dimension of compact subvarieties of AG. So AG star is the Satake compactification, Satake-Bailey-Rell compactification. As a set, it's the union of AG minus 1 dot K naught. And as you can see, it has boundary of codimension. Okay, so this implies that the maximal dimension of a compact subvariety of AG through a generic point is at least G minus 1, because you can just avoid 1. Now I have told you absolutely everything that is known about compact subvarieties. I'm unaware of anything else whatsoever. Let me also state here the theorem of Diaz for MG, 1983. It says that the maximal dimension of a compact subvariety of MG is at most G minus. Okay. I'll write on the next board a little bit about what is known about the existence of compact subvarieties. But notice that the boundary of the Satake compactification of MG, which is its image here, has codimension 2. Again, in at least 3. So this creates lots of complete curves in MG and nothing else. You don't get any growth in dimension of complexity. Okay. I just told you the best known bound for the maximal dimension of the compact subvariety of E through generic of MG through a generic point. There is not known a surface for a generic point of M25. Okay. And I have no bet on whether such a surface is. Okay. Any questions while I'm erasing? Excellent question, which didn't fit on that blackboard. I was going to make a comment about that. So as part of the result of Hill and Sadun, lambda G also vanishes from MG complex type. So this implies, I mean, I wrote it this way, but the correct statement is that if lambda G vanishes, the codimension is at least G minus 1. So this gives a bound 2G minus 4 for the dimension of complex subvarieties MG complex. I'll write this in a second. I was going to make it. So what I'll do now is I'll write a long table once I find this out of what is known about dimensions of complex subvarieties. This will be a table I'll play with the rest of the talk. So if you're taking notes, I'll tell you where to leave some space. Okay. So what I'll do is I'll just write what is known. So in the top line, I'll write this. Here I'll write the dimension of AG, just so that we record it. Here I'll write the maximal dimension of a complex subvariety of AG. Leave some space. Here I'll write the maximal dimension of a complex subvariety of AG through a generic point. Maximal dimension of a complex subvariety of AG indecomposable. I'm running out of space. Never mind. Bad idea. Well, I'll try again. Sorry. There are many things I'd like to fit. If you cannot read them, tell me. The maximal dimension of a compact of AG, maximal dimension of a compact for a generic point of AG, maximal dimension of a compact in AG indecomposable, maximal dimension of a compact for a generic point of AG indecomposable, maximal dimension of a compact of MG compact type. There is some line here which you are not able to see yet. Maximal dimension of the compact generic point of MG compact type. Maximal dimension MG. Maximal dimension of a generic point. Okay. And I'll have to tell you the dimensions of the spaces to learn it, right? So I'll start with dimension 3, as we agree. So what's the maximal dimension of a compact in A3? Well, the theorem of Hill and Sadun, that's luckily there, tells you it's at most. Okay? The bound for the generic dimension of a compact for a generic point tells you at least 2, right? Because the boundary of Satake is 4 dimensions. So that's a lucky coincidence, which means I can just cross out the last label and tell the difference, right? So it's just equal to 2, we don't see. Okay? So this is one case of tremendous success. We know precisely what the answer is. Okay? Maximal dimension of a compact subvariety of A3 indecomposable. And now I'll start looking at the notes because otherwise I'll mess up. Well, A3 indecomposable is basically M3. The Diaz bound tells you that there is at most a one-dimensional compact subvariety. So I can do like this. I can do like this. I can do like this. How about M3 compact type? Well, M3 compact type is A3. Okay. Notice that the dimension of the moduli space in this case is 6. Okay, this is one and only one column that's known to be. This is 4, dimension 4. So the moduli space for Billion varieties here is 10-dimensional. The moduli space of curves of genus 4 is 9-dimensional. These are number 6 here. But what do we know? So Hill and Sadun tell you this is at least at most 5. The bound over there says this is at least 3. Okay. For indecomposable, you take a look at what you get. So the bound, I mean, you throw out the locus of product, say 1 times AG minus 1, right? that has codimension G minus 1. So you always know that this has at least G minus 2 dimensional subvariety for a generic point. So this line is at least G minus 2. Okay. Here, in fact, you can again say that this is most to by Sadun, because the class of A1 times A3 is just equal to lambda 3. And if you have any questions, please ask Rahul. Because this is the class that Rahul is showing with Simon others is non-tautological. So in X4 it is tautological. That's lambda 3. It vanishes in any compact subvariety of A4 indecomposable. So the bound is obtained by plugging in 3 over there, which gives it. Okay. So this is again great success. So it's equal to 2. For M4 compact type, the best bound known is due to Steele and Sadun, so you get at most 4. Okay. For maximal dimension of a compact subvariety of M4 compact type, you get at least 2. Because if you think about the boundary of the Satake compactification, the biggest piece is the image of MG minus 1, which has codimension 3. So we always have complete two-dimensional surface for generic points in MG compact type. G minus 4 is the bound of Steele and Sadun. So the result of Steele and Sadun. I mean, I wrote not the way it should be stated. So the result of Steele and Sadun says that the same kind of bound of codimension holds also for MG compact type. So Steele and Sadun say that there does not exist a codimension G subvariety of MG compact type, which will say you get to. This is an inductive bound. So they basically prove M3 compact type, and then there is an easy inductive argument by intersection of the bound. There is nothing to that. Let's see. But there is some reason you'll see shortly why I don't put it in. Okay. A maximal dimension of a compact subvariety of M4 is unknown. And this is a famous open question. So the famous open question is, can you improve either one of these two numbers, right? So does there exist a compact surface in M4 not known? Anything you can say would be okay. You notice we're already out of the range where we know what happens, right? So this 2 is correct, this 2 is correct. Here we don't. Let's go to 5. By 1. That's what I yeah. But some of this results maybe you wouldn't care so much about the topic. Okay. So let me proceed. I mean, there is a purpose to that. So I wanted to point out that quite a lot is known here, and then very little is known further on. So I won't spend my entire time doing this, but I will. The main results are going to be visible in this case. So in 5, it's the 15-dimensional space. Most 9, at least 4. This is probably at most 5 if you know that A1 times A4 is tautological. I don't know this to be the case. Maybe Rahul does, maybe not. But you would expect 5 here, and you would expect no improvement later on. At least 3. So 6. At least 2. 3. At least 1. Okay. 6. Okay, can we still read? So you see that these numbers, they all diverge, right? There is not a single number we actually know. They're all in the floor. 6, at most 14, at least 5. Here, A1 times A5 is no longer tautological. I have no improvement of the bound whatsoever. All I can say is at most 14. There is nothing better that I can say. I mean, nothing better that follows from what I can say. At least 4, at most 8. This grow by 2 every time. This at least 2 doesn't change because the dimension of the boundary, the codimension of the boundary of Satake is always 3, doesn't change. This goes by 1. This goes by 1. Yeah, it doesn't grow. There's nothing else. Okay. Let me leave some space. Let me put 100 here. 100 is G, but I just want to convey how far this number diverge for large values, right? And 100 is a nice round number. So the dimension of the moduli space for abelian varieties is about 5,000. The dimension of the moduli space of curves is about 300. They are very different. The bounds we get are at most 49, 49 here. For dimension 100, you compute at least 99, and there is a huge gap, not surprisingly. At most 49, 49, you cannot do any better. At least 98, this is for AG indecomposable. MG compact type, it's at most 290, no, not 290, 196, at least 2, at most 98, at least 1. Okay? So this is just to demonstrate the level of our ignorance, right? So somehow here we seem to be doing quite well. Here we're exceedingly ignorant. Okay? There is a bit more known. I'm not telling you about this. So there are constructions of compact subvarieties of MG given by covering construction. So here it's not just less than or equal 98. There is a better bound, which I think is 5. If I miscomputed, maybe it's 6. Okay? But it's not such a stunning number. Okay? To the best of my knowledge, this is everything that is known about maximal dimension of compact subvarieties of AG, MG, MG compact type, AG indecomposable, as of 40 years ago and 20 years ago. Okay? Any questions? Okay. So let me now tell you what's the result. So the most important thing I have to say in this talk, and now you should really pay attention, is this is joint work with Gabriele Mondello, Riccardo Salvacinani, and Jacob Simone. So theorem 1, the maximal dimension of a compact subvariety of AG through a generic point is G minus 1. Okay. So what does this mean? This just means that this line is not greater than or equal, it's just equal. Okay. So with luck, it seems reasonable, I should be able to explain to you how the proof goes with one black box. That's a general theorem, which I will not explain. Notice that, of course, this bound implies something for the maximal dimension of compact subvarieties of AG indecomposable for a generic point. It's between the bound given here, which is G minus 2, and that bound, G minus 1. And I don't have a slightest clue which of the two numbers is actually correct. That would be very interesting, especially in low genus. That would be correct. But I don't know that. Okay, so this is the theorem that is written in LaTeX and checked by all of us. Theorem 2 has maybe a small star, which means maybe it needs something, but we all think it's okay, but I'll remove the star one and on the archive. By the tradition that was initiated by Beatrice, I could say the paper will be on the archive in a week. Maybe that will help us to put it on the archive in a week, maybe not. But I mean, we're basically there. I'm just trying to be cautious in case something happens. This is about the maximal dimension of compact subvarieties, not just for generic points, but overall. Is equal to, and here is an answer, G minus 1, the same number in this, for any G, at least at most 16. Okay, 1 and genus 1 and 2 are always excluded. I don't want to get negative numbers. Do that? And then for higher genus, it's either G squared over 6 or G minus 1 squared over 16, sorry. For any G at least 16 even. Okay. And I can write this as one formula, it becomes unreadable. Okay, so basically it's g squared over 16 to get all the rounding digits. What's the dimension of AG? The dimension of AG is g squared over 2. So the Kiel and Sadun bound is g squared over 2 if it's linearly lower. So this is 1/8 essentially. So let me try to write what the actual numbers are here. So this is 2, we knew this. So here the number is 3. Here the number is 4. Here the number is 5. Notice we're making progress, right? And here the number is something much smaller, right? I'm not going to compute 100 squared over 16 on quantity because I think this will be embarrassing. But 10,000 over 16 is 600, roughly speaking. Yeah, 600 something. 1/8 of that, roughly, right? Okay. Let me say what this yields for modular curve. So this is the corollary of this statement for Dylan variety. That's a cheap corollary. For any g up to 16, you can do a bit better, but I don't want to get into the numeric. The maximal dimension of a compact subvariety of mg compact type is equal to 3g over 2 minus 2. Okay. This is how on earth would that follow from this? Well, this is the wrong statement. So the correct statement is the following. So the maximal of dimensions of X compact contained in mg compact type, but not just that, but such as they intersect the open point. Is equal to g minus 1. All right. Okay. That's the correct statement. So this is a bogus statement. It's true, but this is not interesting. So how do you get this? Well, from here you immediately get this, right? Because the Rayleigh map is an injective at a generic point of mg. It's an injective on mg, right? So we get this immediately from here because the maximal dimension of a compact subvariety of AG is g minus 1. So that's the biggest you can possibly extract in mg. This is a bogus bound because the way you prove this is you just have a subvariety which is contained in the boundary of mg compact type. And I can explain to you by hand waving what this is. Well, we know that M2 compact type is A2, and it's not here, but it has a complete curve. But then you take M21, so you add at 1 point, it's still compact. Then you add another M21, and then you add another M21, and you just glue this thing. And trust me, this is the correct number. Huh? You move all the points free, right? So when you take a bunch of copies of M21 and M22, you get this. So somehow this line should really be 2 lines. It should be like the interesting part. Well, I'll write here interesting. Sorry, here I'll write interesting, right? And then the interesting bounds are 2, 3, 4, 5, and so on. Notice that this stops at g. Well, I wrote 16. If you do the numerics, you get not g minus 1, but still better than still Sadun's bound up to g minus 30 or so. It's not so easy. Practically degree. What is the 16 does not. That's independent. So the statement is that mg compact type always has a compact subvariety of this dimension contained in the bound. There is nothing to that. But I have no idea how to bound this in general. So in genus 100, all I know about compact subvarieties of AG is that most dimension 600, which is higher than the dimension of mg. So I get nothing. I construct that. I mean, my plan is not to tell you about theorem too much because we don't want to go. I mean, we do want to, but I don't want to do it in public to go into Shimura. This is Shimura, and with the intersection with MGs, I don't see it. Nobody raises. And this is a wide open shot. My collaborators may not agree, but I personally would like to conjecture that this bound holds. I admittedly have no indication of this here, except that it happens to be true up until 16. But also, some time ago, Igor Fischer had a preprint on the archive, which had a gap. But the end result of his work was this bound for the compact subvarieties. There is a gap in that preprint that he was not able to finish before his untimely death, and I have no idea how to finish either, but there is some good reason why number D minus one is limited. I'd like to conjecture that this bound is false. There is no reason it's philosophically mathematical. Okay? Sure. No. I mean, the point is the element. So the image, if I have any, what Rahul is saying is that one could make a statement. If I have any compact subvariety of MG compact type, the dimension of its image under the Torelli map is at most G minus 1 or G up to 15. Okay. Maybe it's 15. Okay. But I mean, this is G minus 1. Hill and Sabine bound is 2G minus. So this remains, and even that remains better than Hill Sabine for this one. Okay. Any questions from the results? Okay. So this is the result. Of course, it would be very interesting to try to approach the last question here about modular curve. If you have any ideas whatsoever, please don't take it. I don't know. I mean, obviously, we are thinking. Here, and we'll see what happens to the table. But at the moment, that's all I can. Question? I'm unaware. There are various states. I mean, the Satake compactification is the smallest compactification in various senses of AG. For MG, you can make some statements, but anything they go all the way to pure bonding. I'm unaware. There may be something wonderful that I will have. Okay. To me, somehow the most embarrassing maybe is the last one. We don't know whether M100 has a complete fit. The reason I wanted to leave the space here is because you can see that at genus 16, the numbers here start to diverge, right? So here you got a 15 dimensional subvariety, right? While here the maximum dimensional subvariety for a generic point is only 16. That's the first genus where there are compact subvarieties of MG, of AG, which do not go for generic, right? That's the first genus that happens. There is something interesting. In genus 17, this is still 16, well, this is back up to 16. So it means in A17, there is this huge family of very moving, very general subvarieties to generic points. There are also constructors of Kimura varieties, which happen to have the same dimension. If you go to genus 18, this goes to 17, and this goes higher. Okay. So something interesting. I don't know any meaning to this except numerical. Notice these are not less than equal. This number. So this is something. Okay. Level structures don't play any role whatsoever, because if you have, these things are insensitive to finite covers, right? If you take a finite cover, you have a variety upstairs, you move it to a variety downstairs, and pull it back. Nothing changes. You can also ask about non-principal polarized given varieties. Still okay. This is a very rough measure of failure of affinity or failure of verticality.
You can level structures with some topic on the interior and then you boundary.
I'm sorry, by level structures for ET, I mean, yeah. And then complexity. That's a different question. But if I take, if by level structure, I mean a finite subset of L and points, nothing happens, right? What to tell you anything? I have no idea. There is no, I'm unaware of any result for the Pring locus. So the best I can tell you, Pring locus is inside the AG for that one. Any other questions? Okay, so I'd like to prove theorem 1 for you, more or less. Okay, so I think there are many graduate students in the room, so I'd like to make a more personal story of how one proves the theorem. So here is a motivation. Is this space. But this is nevertheless a motivation. This is how we started thinking about it. This ties in nicely with what we spoke in some way. So you take a locus in AG, so take E to be some sufficiently general elliptic curve, right? Take the locus E times AG minus 1. That's the locus inside AG. It has homology class up to a constant factor, which is irrelevant, lambda G. Notice this is always tautological. You can ask for who these philosophical reasons why you would think this is tautological, while A1 and AG minus 1 is not. But this is a tautological class. And of course, you know that this class vanishes on AG, right? This is easy to see. You can just take E, you can just move it off to the boundary. You can move it off to I infinity, the boundary point of A1. So of course, this is a zero homology class because it just flies off to infinity, right? It flies off. Fair enough? Okay. Suppose for contradiction that the maximal dimension of a subvariety of AG compact for a generic point is at least G. Okay, I want to prove this is impossible. So take the compact G-dimensional through one point of this locus. So this is the fact. Okay. If they intersect transversely, so let's say there's some point. And then, of course, you would see that lambda G dot Z is non-zero, right? Because if they intersect transversely, you get a positive intersection number, and then you get a contradiction. Well, you think of this in an office, in a very nice office with a view of La Sapienza University of Rome. You think this looks very promising. You go home, have a nice dinner, try to write it up. You realize that, of course, you need to prove transversality, but that's be fine. Then you realize this is not so good because, yes, they do intersect transversely at some point P, but maybe they also intersect non-transversely somewhere else. And maybe there the contribution to the intersection number is negative. So who knows what happened. And then you go back to the same office the next day. You realize that lambda G was completely immaterial here. So somehow the transversality seems to be the important thing. You don't want to do intersection numbers. So you crash some part of this argument. There is a reason why I'm telling you this. And it's not, I'm just telling you how to fail to put theorem 1. I'm trying to tell you how to prove theorem 1. How to fail to put theorem 1 is an exercise we engaged in for a while. But it's somehow learning it. So you don't care about this. So you say if the intercept transfers to a P, then for any E prime in A1 close enough to E, the intersection of your Z with E prime times AG minus 1 is also non-empty because it's a complementary dimensional thing. So if the intersect transverse, you can move one of them, they will continue to intersect. Okay. So all you need is not really transversality. You need to know that the intersection is dimension 0 at this point. So think about this here. You don't care about that. Where is the complex set? Okay. Then this means that if I move E over A1 in some neighborhood of E, I still have the set. And the set of E such that Z intersects E times AT minus 1 is a subset of A1 is open, right? Because I can just move nearby. It's analytically open, but this is clearly an algebraic condition. It's just not empty. I mean, if I have one point where the intersection dimension 0, then locally they will also intersect, also in dimension 0. And all the cases that they don't intersect. That's an algebraic condition. So this is as a ratio. Okay. But then this, of course, does not contain a neighborhood of infinity. Well, I'll write it down. I infinity. The degenerate means to turn that one bar. So consider. Okay. Make sense? So I'm saying if you have a compact subvariety which intersects a product of a fixed elliptic curve and AG minus 1 in dimension 0, then it will continue to intersect in a small analytic neighborhood. That's an algebraic condition. So it's the Zariski open set in A1. A1 is a projected line. Any Zariski open set is a complement of the finite many points. But then Z is compact. So obviously, if this goes up to infinity, I lose the intersection point. So then I must have lost the intersection point close enough to infinity. So that's a condition. Make sense? You need to be dimension 0. So yeah, exactly. So you start thinking more about this. So you replace this transversely, intersect in dimension 0. It doesn't mean anything. But if you have dimension 0 at one point, then that's the set you can look at. Yes. Okay. So then this is the next day. You have 5 more cups of espresso in your office in your panorama. You go home. You write this more nicely than I'm doing this now. You realize that you need precisely to check that your given compact subvariety intersects this in dimension 0. And of course, you realize it's not going to work, which is not actually how we thought about it. We knew this was not going to work. But remember that the moduli space of abelian varieties, which is no longer on the blackboard, is a symmetric space. So if I have one compact subvariety, I have many more by Hecke translation, by Hecke action. So Hecke action just means I take an element of sp2gq, and this will map a compact subvariety to another compact subvariety. So of course, sp2gq is dense in sp2gr. So you start by saying, okay, I don't know about this, but let's act by sp2gr, maybe keeping the point of intersection fixed, so we act by UG, and let's make sure that the intersection dimension 0 by looking at the tangent space and checking transversality. You try doing this, you take a flight back to the US, doesn't work. A couple months later, you're back in the same office with your 5 more espressos. You spend a week trying to prove that for any G-dimensional tangent space in AG, you can add by an element of UG so that it will become transverse in the tangent space to this. You spend a week doing this, you make some progress, you get some results, you realize this is very close to what Thiel and Sabina see, and in some way you continue failing. Then you start talking to people. So you talk to Salim Tayouk, who should be promptly the same, but even though he was not on the board. Then you talk more, and then eventually you talk to Jacob Zimmerman. And then it turns out that all this can be made to work by using proper machinery from weakly special subvarieties and subplots. Okay, so I have about 8 minutes to tell you what the statement is. What is. So what you actually, so here we go to proof of theorem 1. And the proof is just do this, but enhance it by some high power method. So what you use is you use the weak X channel theorem, which is used to mock Thiele and Zimmerman. But you actually use some version which appears in the paper of Khalifa and Urbani. It says the version that I'll get, this is the black box. But if you know what weak X channel is, you know how it works. If you don't, ask them or Bruno. Okay. And maybe also not that. It says the following. Suppose X in V in AG irreducible compact. And generic point of Z has huge simple algebraic monodromy. Let F inside AG be the smallest Kimura variety containing it. I won't tell you what Kimura varieties are, but you should know that if I take a very general point of AG, there is no Kimura variety containing that. I take a fourth generic point, there is no Kimura variety containing that. If I have some other Kimura variety, in the morphism of Kimura variety, that has an unlikely, an atypical inspection, such that the dimension of the Z was the dimension of F then there exists an element right there at the intersection this is think of this as SPTGQ, a smaller C. It's part of this is a Kimura group of S, so for us it's really enough to think of it as SPTGQ. But if this is non-empty, of expected positive as a component of expected positive. Okay. I won't fully try to unravel what this is because I have about 5 minutes and I want to say a few more words about how the proof goes, which I realize may be lost in people who are less familiar with Kimura variety. So what this says is basically the situation we care about, I wrote a slightly fuller version because we need it. What this says at the end of the day is that if you have any, suppose V is an irreducible compact subvariety of AG, which is not contained in any Shimura subvariety. So F is just AG. Then it says that I can find an element of sp2gq, so that this translate of sp2gq will intersect the image of some other Shimura variety. This Shimura variety is my elliptic curve times AG minus 1, which is a Shimura variety. If I apply a suitable rational symplectic transformation, it will intersect Z, and it will intersect it in respect of dimension, which is going to be zero. Take this, plug it into this attempt, you're done. Okay, so theorem 1 is done. Modulate big black ball. But there is no X here, there should be Z. Okay. So this is my lack of preparation, right? So my compact subvariety is always Z because at the beginning of the talk I care of zero X. So, that's the Heck expression. And then so this is S, if S is AG, this is SP2GQ. And then being somewhat sloppy because of course this does not act on a subvariety of AG, it acts on its universal cover, and then I have to project down. So that's the Heck expression. So this is what this, and this F, I'm writing as a morphism of the Shimura variety. If S is AG, so if F is AG here, then the only case I need for theorem 1 is if this is AG, and this is E times AG minus 1 embedded in AG. That's all I need for theorem 1. That's obvious. And this is all fine, right? I mean, so what I really needed, so this was the intersection to have a point of expected dimension 0. Yeah. Good question. That's probably yes. The statement is not quite stated, I think, but this is a very interesting question, which leads to some questions I don't know. So, what's
anything? It comes on the moduli complement.
There is an assumption, yeah. But if Z goes for a generic point, I mean, this is what an actual takes place for subvariety very general. And if you go through a very general point, and this is a typical statement, if you go through a very general point of incidence, very good question. So somehow you would like to say, I mean, if you're very optimistic, okay. I won't have a chance to say much to write anything. So let me say, okay, so what happens then is after you do this, and you're very happy, you have a midnight conversation with Jacob Signal, which is very early. And then you start thinking, do you really need to be compact? And then you try to think, oh, maybe you could prove that for any d-dimensional subvariety of AG, it can be made transverse to P intersect AG minus 1 or something like that. Then you start wondering whether this has any implications for the homology range of AG. And then some of the implications seem remarkably strong. So you go to bed not really believing stuff. And then, of course, you come up with something. So basically, there are complementary dimensional even higher Shimura subvarieties of AG would not. Right. So the most optimistic thing I have ever said in this direction was, if I have two subvarieties of AG of complementary dimensions, they must be the same. This is some kind of huge quantity. That's false, because it just have Shimura varieties which do not. Right? If you're thinking, oh, just take E times AG minus 1 and E prime times AG minus 1, that's false. They do this because they intersect from E times E prime times AG minus 1. But there are Shimura subvarieties of higher than complementary dimensions that do not. So there is more of the story which I don't. Okay, but I'm about to be over time, so let me take 2 minutes to tell you how to prove theorem 2. So what does this tell you? This doesn't prove theorem 1, this proves more. This somehow proves that any compact geo-high dimensional subvariety of AG must be contained in a proper Kimura subvariety of AG. Kimura subvarieties can be products of Kimura variety of reducible, plausible, whatever you want to call them, Kimura varieties. They can be compact or non-compact. So you first prove a statement that if you have, which is the same statement, but this is y or this. So here you can see that you can replace AG by any other Kimura subvariety, and you'll still have some kind of transversality of integral. And with some more work, you can show that if you have any non-compact Kimura subvariety of AG, the bounded theorem 1 will still apply. So if I have a non-compact Kimura subvariety, I don't gain anything. Okay? Then you prove that if you have a product of Kimura varieties mapped into AG, then each individual Kimura variety maps to some factor of AG. So at the end of the day, this allows you to just say that non-compact Kimura subvarieties are useless. They don't improve the bound in any way. So then at the end of the day, what it says is if you want to prove theorem 2, you have to classify maximal dimension, compact Kimura subvarieties of AG and find out what their maximal dimension is. Luckily, there is a list of symplectic representations of Kimura data, which you can find in a suitable set of lectures by Mill and elsewhere. And you go down the list and you try to see which ones give you high dimensional compact subvarieties of AG. You do this. This is for single representations, and you take products, you get a bit more. That doesn't help. So G squared over 16 is the maximal dimension of a compact Kimura subvariety of AG. That's what it is. And we moreover know what Kimura data corresponds to. So the statement of theorem 2 is not just to say what is the maximal dimension of compact subvarieties. It actually tells you what are the maximal dimension of compact subvarieties. They're compact Kimura subvarieties. I can tell you what the Kimura data looks like.